two, one. Hello everyone, welcome back to our YouTube channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, Max, who has completed the course ROS 2 Basics in 5 days. And at the end of this course, we have a project available in order to get a certificate in which you have to program a real robot. So that's what we're going to be seeing today from our students. So hello, Max, how are you?
Hi, Rodrigo. I'm fine, excited, looking forward for the project.
Great,
So,
great.
fingers crossed.
Perfect. So whenever you want, you can start sharing your screen and show us your project and explain how you've done it.
Okay, let me start sharing my screen. Can you confirm you can see everything?
Yes, I can see the robot and the IDE.
Great. Yeah. So I will just show the how the robot works, and I will be providing some descriptions while it's doing.
Okay.
So in the beginning, you can see that the robot rotated. It found the nearest wall. Then it rotates 90 degrees anti-clockwise and starts the wall following behavior. So you can see that when the robot gets closer to the wall, it bends the other side, and then if it gets further from the wall, then it tries to direct itself to the wall. A few seconds ago, we saw also that when it saw like a wall in front of it, it started like making a more fast rotation towards left, so it can continue following the next wall, right? And we can see right now the robot just making this behavior. In the console below, we can see at all every I think second. We can see. I think it's actually like more than one every second, but yeah, we can see the feedback. So basically, every time we can see the total traveled distance. And now the robot finished with like feedback, which is robot made a lap. The total traveled distance 5.4 meter. And here the call finished. So that's like the expected behavior, what we wanted from the robot, if this makes sense.
That is awesome. That was really impressive, really fast, and just did it so well and so quickly. Awesome. That's nice.
And do you have any questions regarding this, or should I continue with?
Yes, I'm curious on how you did it. So just could you explain us how you did each one of these sections, please?
Yeah, so I will now focus on the IDE. So I will describe all the sections that actually started at different stages. So maybe I can actually start from here. So here's the wall finder behavior, right? So when the robot starts, it's like I'm creating like a service find wall, creating all the publishers and subscribers for that, creating all the necessary callbacks. Actually, this is not needed here. It's just a leftover. And here's my basically find wall callback. So whenever the action service is being called, then this is what's happening. So I structured into like few sections if everything is in the same callback. So the first behavior is like find the nearest wall, which I'm doing by finding the minimum value across all the values in the laser scan array. So when I'm like, I have the topic for the, I think it's the called /odom, right? So the odometry, no, sorry, that's actually the scan topic. I'm getting all the values from around the robot, and I'm finding, okay, where's the shortest ray, right? And based on that, I'm getting the you have here the while loop for that. So I'm basically, I have like all the values. I'm trying to find the index of the shortest ray, and then I'm rotating the robot so that the index in front of it actually points towards this like front of the robot. So
all right, yeah,
do the rotation as long as the index in front of the robot is not the shortest one. I have also like this functionality that if the robot is slightly rotated, let's say to the left from the center or to the right, it actually adjusts to where it should rotate. So it can also rotate clockwise and anti-clockwise to speed it up, because otherwise sometimes it would happen that it has to do, let's say, a 340 rotation instead of like just 20 degrees. The next step, I don't know if it was visible enough on the initial demo, but the next step is that whenever it detects the motion and it rotates towards the nearest wall, it has to go to the wall to a set distance. So what I have here is basically like another while loop, which is constantly measuring the distance to the wall. And if it's too far away, then go forward. If it's too close to the wall, because let's say there was a interruption in the receiving of the topic, or there's like a different problem, then it can also go back from the wall. So it really tries to adjust to be exact at the same to be at the exact position from the wall. And the next step is basically to rotate, to prepare itself to start the wall behavior, wall following behavior. So I'm getting the current rotation, which is like, let's say 0 with respect to the wall. I'm adding the 90 degrees offset, and then I'm doing the rotation. So the behavior is quite similar as to the getting closer to the wall, but instead of making like a linear motion, it's doing an angular motion.
Right.
And then the next step is the wall follower. So it's a quite basic, let's say, algorithm. I'm measuring all the time the reading from the right of the robot, so the distance to the wall on the right. And if I'm close, I have like two main conditions. If I'm further from the wall on the front, so let's say it's very far away, I'm just doing like a basically comparison. If I'm close to the wall to the right, then go slightly faster on the towards left. If I'm far away from the wall, then I'm going to the right. So it's like basically, let's say, almost a snake motion.
Yeah.
If I'm close to the wall, then I'm dropping the speed in linear. So I'm trying to slow down a bit, and then I'm going as fast as I can towards left. So I can make a left turn. And then, in another loop, this happens like all the time, right? Because it's a callback. So whenever I get a value, when I have again, like, okay, there is like the front of me, the front of the robot is clear enough, then I can go start doing exactly the same behavior as before. Get the readings from the right side of the robot and decide, okay, should I go like a bit more faster on the left or a bit faster on the right? And the last section of the code is the action server, right? So what I did here is like I have a callback, right? It's basically like getting the necessary data. So I mean, basically here is like just get the goal. I'm getting the first point because I need this to know where my lap will start and my lap will finish, right? Because the robot most likely won't ever be exactly at the same spot. What I did here, that when I got my first reading, like let's say in the like 2D space of the grid here, I created like a small square. And how this works is that, let's say that as you can see on the screen right now, here I have my robot somewhere in the grid and the traffic.
Yeah.
And I'm creating like a small square around the robot of size like 10 centimeters, right? And that's my like starting point. So my point is not in fact like a point; it's more of an area. But that's only to provide like a way that the robot, can be close enough to the finish line or like start line after it makes a turn, so it knows, okay, I actually like finished my lap. To be fair, I had also like a problem with this because it really depends on where the robot starts. Because sometimes, for example, if the robot ends up in one of the very corners of the, let's say the grid, the robot won't ever make it there, right? Because when it tries, I don't know if you can see my mouse on the screen, it will try to go more to the like interrupted line, so it won't ever reach this corner here. So I had like another like break condition here in those lines, so 89, 91. If the travel distance is more than like 6 meters, which is basically already a bit more than we want, because from my like experiments, most of the times the full lap took like around about 5.4 meters. So it's like just, let's say, safety, so the robot doesn't run indefinitely, making loops, right?
I see.
And while the action is happening, so when we are calling the action, okay, hey, we want to have now this behavior, please measure all the points and so on. Yeah, I'm collecting like every time, whenever, every like few, like per given like timestamp, I'm like collecting the next point where the robot is, and based on the like those differences between all the points, I'm like calculating the total distance. And obviously, the whole runtime of the robot, you can see like the feedback registers being also sent in the action service. So we have also like always the current total values, like you can see like 525, 540, and so on. So we are always able to know how much distance the robot made while the program was running. I think this would be it. Or do you think I could or should explain some areas more specifically?
I mean, no. Let me say first of all. Let me change your screen here. Do you mind stopping sharing your screen so we can
Yes.
now? Let me fix this right here real quick. So congratulations, that was a really nice project. I really liked how quick and efficient it was. A lot of people are scared when they move on to the real robot to provide quick velocities, and I can see that that was really nice. I really liked your solution, for example, to find a. I'm sorry, are you there? It seems like you froze. Oh, seems like Max froze here. But anyways, let me keep going. Maybe in the meantime he'll return. I was saying, and Max, of course, you can see this later in our YouTube channel. So I really liked how you solved the TF. I'm sorry, not the TF. The one lap issue, right? And you explain how in the corner you might have some more issues. Oh, looks like Max has left the call. We'll wait a little bit, and oh, he's back. All right.
Sorry.
Don't worry. Yeah, I was. Oh, sorry. I was kind of wondering why you froze. So I was just explaining to the audience and to you afterwards. You can see it. That I really liked how you solved, for example, the one lap issue, and how you can have some issues when, for example, it starts at the corner because of the movement. So at that point, there are decisions you have to take, whether to modify the behavior of the robot in order to make that happen. But since you've done this so well, let me recommend an idea. And of course, this isn't part of the course, but it's an incentive for you to see how this can be solved in another way. There's another thing called transform frames in ROS and ROS 2, and these define things in the world. For example, in the robot or the robot that is seeing a charger, things like that. So, and you can publish these things. So I recommend you take our TF course so you could think on how to solve that issue without modifying the behavior or anything, and while using TFs. The point is, you could publish a TF and then follow that, and then that way you can approach it however you want. So it's a suggestion in order to address that specific issue you mentioned. But other than that, I mean, it's a really nice behavior and code. I just have one question, and it is that in all of your notes, actually, I noticed that there are sleeps of 1 second just scattered around. What is the reason for those sleeps?
It's more to not like spam the CPU with like too many actions at the same time. So that's like, let's say, my usual thing, because if we are like a while loop let's say while true, and then nothing happens inside, let's say a print statement, there's like lots of CPU power wasted on like
I see.
Unnecessary like things. So it's always like, at least that's like my understanding. It's better to just do nothing and really like just wait, which just like reduces a lot of load on the CPU.
Right. Yes,
But
that's a good
yeah,
idea. You could
but
though make the node spin slower. That's a way you could improve the if you're concerned about sort of CPU usage. But for a simple why I'm saying this is I don't think it's I mean I understand that and it might be even better for you to like kind of structure it in your head. But you had to be careful once you start adding a lot more nodes, because maybe one of the other nodes requires something while the other one is sleeping, and these things can create issues. But okay, I see what you're doing, and then to sort of do breakpoints in the process, right? Okay, all right.
Yeah, but I think it would make sense to just spin the nodes with like given frequency or whatever. So
Yeah,
that's
but
like
then you have to manage the how fast you're,
Yeah.
processing the lidar data, for example. Maybe it's not quick enough to take action. So I understand, and there are ways to solve this, but this is way too complicated and not part of the project. This is just to get a sense of the basics. So, I mean, other than that, it's a really, really nice project. So I just want to congratulate you again,
Thank you very
Max,
much.
and yeah, 10 out of 10 for me.
Thank you.
All right. So I just want to mention that to whoever else that is watching the audience, I just want to invite everyone to do what Max did here, to complete the course and then to go ahead and present with us what you've learned on a real robot. This way, you can solidify your learning and show people what you've actually learned with our course. You can share it with as a part of your portfolio, and you can get a certificate from us because we want to actually see that people take something of value out of our courses because our certificates mean something to us. So I invite everyone else to do what Max did here. And Max, thank you again for your presentation, and we hope to see you around for another course presentation.
That's the plan. Thank you very much.
All right. Well, everyone, that is it from us here at Becoming a ROS Developer. We'll see you today. We have 2 more presentations, so we'll see you guys for those ones. All right, bye, guys. Bye-bye. All right, cool. Done.